This lesson is about understanding the nomenclature of the X-ray emission line. When we read a paper about X-ray from the analysis of art examination, we find this name K alpha, K beta, L alpha, L beta. Let's see what they relate to. We start this lesson reviewing this scheme, this atomic structure, and the description of the photoelectric effect. The photoelectric effect is the origin of the X-ray emission lines, those peaks that we see in our XRF spectra. What happens is that we have incoming X-rays from the X-ray tube. These X-rays can kick off electrons from the inner shells of the atom, so generally K, the K shell, the L shell, the M shell. What happens is that since this electron has been kicked off, the atom has to fill that vacancy, so we can have that an electron of the upper shell will move into the inner shell. So, for example, we can have an electron from the L shell or an electron from the M shell. What happens is that when an electron from the upper shell goes into the lower inner shell, in this process, in this transition, the electron releases energy in the form of characteristic X-ray. These are the ones that we actually measure with our X-ray spectrometer, and we can use them to identify the elements, because the energy of these transitions, of these emission X-rays, will be specific for the different elements, the chemical elements. We like to represent this electronic shell, so we have K, L, M, N, O. So it's the same of the atomic structure we saw here, but this one is more tidy to represent the process. The nomenclature uses this scheme. The first letter is to indicate the shell that will be filled. So, for example, imagine this transition. The electron in the K shell has been kicked off, so we have the electron in the upper L line that goes into the K shell. So this transition will be called transition K, so K to indicate where the electron is going, and then we can have alpha, beta, or gamma. We use alpha to indicate that the electron is coming from the closest shell. So if we have a K here, L is the closest. So this emission line, so this X-ray coming from this transition, will be called K alpha. If the electron filling the K shell is coming from the second closest shell, in this case this one will be called K beta, and we will have a different energy. We can tell basically from this diagram over here, from this illustration, that the energy of the K alpha, so if imagine here these are the differences in energies, the K beta will have higher energy of the K alpha. Then we can name all the other transition. So imagine that the electron has been kicked off from the L shells. This L shell can be filled with an electron coming from the closest shell, so the M. Consequently, this emission line will be called L, because L is the shell where there is the vacancy, followed by alpha. So we have an M electron going into the L line. If this vacancy is filled with an electron coming from the second closed line, so the n shells, then we have that this transition is called L beta, and then we will have the L gamma, where the vacancy in the L shell is filled by an electron from the third closest shell from the O shell. This is an example of a typical XRF spectrum. So in this case we have tin, is just a cube of tin. The cube of tin will show this line, so we have one here, another one here, and two small over here. The K alpha, you see, has this energy that is in keV over here. The K beta has higher energy. The ratio between K alpha and K beta is about 1 to 6, 1 to 5. So you see this one is basically 5 times stronger than the K beta. The K alpha and the K beta generally are the most intense, the most strong lines. Then the N lines will be less strong. These lines have been measured, these emission lines specific from the K alpha, K beta, L alpha, L beta, L gamma for all the elements have been measured. And so we can use these tables with this information to read our spectra. Over here I propose you three resources. So let's start with the first one. The first resource that we suggest is our table XRF peaks of chemical elements. So sometimes we call it lines, sometimes peaks. In this table are listed just the elements that are important for art examination. So for example, let's see, we have magnesium. Magnesium, we can tell the K alpha line. K beta there is not, because they are so close together that we cannot distinguish them with our instrument. Then the K alpha and the K beta start to be separate with sulfur, so we can tell them apart. Then we can scroll this table and, for example, we go over here, we have silver. Silver has the K alpha, K beta, and then we have L alpha, L beta, and L gamma over here. And so for the other elements, we have the other lines. So these are just the elements important for the art examination. Then we go into something else. Okay, this one online from Oriba Giovanni Von. This table shows for the elements all the peaks with more precision. So we have 2 decimal number for all the other elements in the periodic table. A further resource is from the Lawrence Berkeley National Laboratory. They made available online this table where we have all the emission lines in increasing order regardless of the chemical element. So for example over here, let's magnify so we can tell. Okay, so we can tell. So we start with the first line. This one is an electron volt. So we have a 54 electron volt. This one is related to lithium, and there is the K alpha of lithium. So then they are in increasing order, so we can scroll it. Let's say we go up here, and so we have basically this one will be 2 keV, and this from zirconium L alpha, and so on. So this kind of table is useful when you find peaks that you don't know what they could be, so you go and see which element this line belongs.